So today I'd like to present my recent research topic on semantics-native and nouns-driven secure communication. And this is going to work with Professor Matt Bennis and Professor Jihong Choi and Professor Sung Kim. And oops, I think. And it's possible to. Yeah, I think it works. Yes, and Professor Jihong Kim with the Korea University. All right. Before going into detail, I'd like to first share some backgrounds in the context of machine learning for communication, say MLC. So one, conservative direction for this type of machine learning for communication research direction could be AI-aided communication, direction and principle. So at least many of the industry partners and academia have already agreed on the fact that the next generation communication system will be at least based on AI. So in other words, the degree or the level of its exploitation will be depending on their preference. And then given this, probably the most conservative way is to apply the machine learning techniques and tools for optimizing the already prepared and structured communication architecture. On the other hand, the machine learning itself that has more potential in dealing with multimodal data and other, rather than compressing, it can provide some good performance in generating some images, in other words, imaginations, and playing some games as we have seen in the AlphaGo example, and many more. So given this, we can also conceive a bit ambitious goal that could be AI native communication architecture. So already in the domain of physical layer and the MEC layer, the AI native approach for designing communication systems have already been proposed. For example, the end-to-end communication operations can be replaced simply with a single neural network under the structure of the autoencoder. So this end-to-end feeding forward operation of the neural network can be regarded as an end-to-end communication. And actually, this is a neural network itself. And neural network is a functional approximator. So not only it can approximate not only single functionality of the communication, but also many others. For example, it can mimic the operations of the source coding. And then at the same time, why not channel coding? Then it naturally leads to the joint channel and source coding, right? So JSCC. And then extending this idea, we can also approximate other functionality, integrate them together, because neural network itself is a functional approximator itself. So the natural extension could be, let's say, what could be this alpha factor? So given that, recently the machine learning models are able to produce, for example, extremely high fidelity images by using some natural language prompting. For example, this one image has been drawn by the DALL-E 2 model by simply writing down the comment that is looking through a glass of red wine while driving on the highway. Then you can see these types of high resolution and image. And then at the same time, for example, another large size language model, which is called GPT-3, is able to provide some your coding assistance role. For example, you can simply write down the API of the code by using natural language, so that the GPT-3 can generate the correct syntax of your code. So given this, we can be even more ambitious. For example, we can aim at enabling and implementing semantics-native and say reasoning-driven communication systems. Actually, in the context of our communication theory, at the very beginning of the communication, the Shannon and actually the Weber, okay, the levels B and C are about, may sound a bit less technical, which is about, firstly, the level B problem is about to deliver the meaning correctly. And the last one is to make the communication effective in the given task. So up until now, the correct and proper technical tools have not been identified, so it has been passed over in silence, literally. spurred by the recent advances in machine learning and techniques, perhaps it's time to tackle those two ambitious questions. So in focusing on, for example, the level B, to deliver your intended meaning accurately, the intended meaning is important. So in that sense, for example, the words include multiple meanings. So to deliver your intended meaning, then perhaps you may need to reason about something about your listener based on their communication context or their hypothesis. For example, if I alter some messages, then how would the listener would respond or understand would be another key factor. For example, depending on the cultural differences and then educational backgrounds and many more. Even if we hear about the same word, the understanding and the context might be quite different, right? And then on the other end, focusing on the third problem, level C problem, then to maximize the given test effectiveness, actually that's a future event. So to maximize it, literally and ideally, we need to predict the future based on the current communication to carry out my current communication transmission decision as an example. Oops. So these types of questions and the corresponding answer would be related to the types of causal reasoning. By understanding the cause and effects relationship, we can answer those questions rather than the statistical relationship that is actually based on at least the foundation of the current communication system and or the current actually deep learning itself. So to enable so if we enable the causal reasoning, then the benefit would be multifold. For example, based on my two favorite movie, Ready Player One, we can imagine metaverse-like scenario where there exists no latency, even if we interact with the person far away from, for example, my colleagues in Australia, which is the opposite side of the world, right? And then we can thereby enjoy the extreme rate of the compression, and then thereby we can also communicate proactively. On the other hand, we can also imagine another type of scenario, which is a bit similar, but still different. That is another movie, really report-like scenario where we can implement, for example, the exact digital twin of the real. In that case, we can even predict the future events rather than the communication scenarios. Then upon which we can imagine the corresponding, the task-related issues and events so that we can skip unnecessary communication. In other words, as long as I can predict, then I can skip all the communication. That's even beyond the level of compression. And then, so the communication roles might be, at least in part, related to communicate to a forecast. So given this, actually, this vision will be enabled and achieved as long as the current machine learning and or some other tools can effectively solve and enable the causal reasoning operations. But unfortunately, causal reasoning itself is somehow holy grail, even in the domain of machine learning. So as an example, the well-known guru Yosha Bengio and inspired from Daniel Kahneman, he has identified the two different levels of machine learning. One is a system 1 machine learning, that's the current deep learning, and the other level is a system 2 machine learning. So simply speaking, given their different and multiple differences, among which the one most critical fact is that the system 2 machine learning is able to identify, understand the causal relationship. They may not include, so causal relationship is simply speaking directional. On the other end, the statistical relationship, in other words, the dependency are bidirectional. So given this, causal relationship can lead to the statistical relationship, but the other side is not true. So given this nature, identifying the causal relationship might take more time and more effort. But once we can achieve that modeling, then we can straightforwardly lead to many other, enjoy more than several food. That's it. have no idea how I can minimize it. Anyways, okay. So given this, there are probably at least the state-of-the-art machine learning and deep learning community has already very recently achieved one possible way to achieve this and enable this causal reasoning. So one possible way is surprisingly and it's simple. That is to increase the machine learning model size extremely large. So, for example, the typical, say, machine learning model, the CNN model, that is a ResNet 15 model, that consists of only 23 million parameters. On the other hand, when you say large language model that is capable of, say, causal reasoning operations, then that's the order of 100 billions. So but the order of magnitude changes. So given this, if we increase the number of parameters extremely large, then surprisingly, the machine learning model itself is not only understand the statistical relationship, but also is capable of understanding and exploiting the causal relationship. So one example is that recently, a couple of, say, a month ago, one Google researcher, Lemoine, was fired because he claimed that he's developed AI chatbot, which is named Lambda, is sentient. Which means that literally that model has passed the Turing test, right? Even if they haven't measured it. So, and that's one example. And another one, this is a GPT-3 example. Actually, GPT-3 is a 2-year-old model. And then given this, recently, people have tried some interesting experiment. That is, by default, they focus on one task that is difficult to be solved by the GPT-3. But given that the same problem, they ask a question in a different way. Just let's think step by step. Then it starts solving the problem, which means that even though the GPT-3 model itself cannot explain, how I learned the causal relationship or not, but it implicitly and already understand how it goes and everything, and it even understand what thinking step by step means, thinking slowly means. And then the most state-of-the-art model by Google's Pathway Large Language Model is able to do a counterfactual reasoning. For example, given this scenario, he or she can conclude some counterfactual, say, reasoning result, which could be seemingly the highest level of reasoning one might imagine. But given this, the problem is that even if the system 2 machine learning and/or the causal reasoning capability has been achieved recently by the extremely large model, the straightforward drawback and limitation could be to achieve that goal. It requires extremely large amount of computing power. For example, over 2,000 TPUs, the state-of-the-art AI native computing engine, and over 1,000 CPUs, and with the memory size that correspond to 540 billion parameters. Yes, so which means that perhaps we have built an ENIAC computer, but it is not capable of and handling only using our mobile phone desktop. No. And on the other hand, another problem is that, for example, back to the GPT-3 example, by default, the GPT-3 model wasn't able to solve the problem, so the accuracy was below 20%. But by changing your prompting, the way of asking the question, the accuracy is changing, right? So the bright side is that there is a way to improve and increase your accuracy without any further training. The dark side is that it means that we have no guideline. So it's just a black box function, and we need to find a way, trial and error, and on the fly. On the other hand, this is another amazing example drawn by DALI and one of the recent state-of-the-art model, Stable Diffusion model, with the same prompting message, Taj Mahal made of cheese. Then you can see these high-resolution fidelity images that can be imagined rather than combining the existing forms and the patches of the images. But the problem is that given this the same script, the images, even if it is seemingly in looking beautiful, they are totally different, right? So we have no controllability of generating our desired messages and or the images. So in the context of semantic communication, there's no guarantee of conveying our intended messages that can be understood by your listener. So given this, let's also, in the meantime, there has recently been more than several semantic communication related works, so among which I'd like to categorize them into three major groups. One is a filtering based group. So in this case, for example, the goal-oriented communication works are literally related to goal-oriented evaluation in terms of timing and then incorrect information period and many more. But this is somehow overlooked the importance of semantics or the meaning itself. So timing evaluation, that could be regarded as some metadata or the flag, but itself, it does not include any meaning of the message itself. On the other hand, the other ways could be some compression examples by utilizing the meaning similarity. For example, you can send a bad image by instead of sending the image, but you can send your text messages. So across different data domain, you can enjoy the benefit of compression, which is a bit different from the conventional source coding. But actually, in this case, again, the problem is that it is not controllable. So given the same bad text messages, there might exist multiple different ways of generating the images. For example, bat has the meaning of one animal. At the same time, it also has another meaning of an object in baseball game, right? So it is context agnostic. So the compression can be achieved significantly, but sometimes the intended message delivery may not be guaranteed. The last part could be the knowledge-based ones, probably based on and relying on the recent success in the large language model that can be seemingly regarded as one, say, world model that can answer any questions, that can model any events that may happen in reality. But the problem is that, as I told you, building and developing such a model is too costly. And then again, the controllability is not guaranteed. And then given this one, the existing works have implicitly assumed that that large language model is shared across all the communicating agents and parties, which means that it is only related to, say, pool-based communication scenario, where if you want to communicate with each other, you need to always ask your, say, base station and then wait for their responses, rather than interactive communications. And another, so given this three categorization, one limitation or some issue could be is that the definition of meaning is unclear. In other words, meaning has multiple meanings. For example, when we look into the first example, the valuation and filtering based example, the definition of the semantics would be highly related to that definition in the domain of logic. So in the domain of logic, the definition of semantics is actually the truth table, the truth itself. So in other words, the valuation of your logical expressions. On the other hand, if you look into the compression example, then that definition of semantics are more related to that of vision and or the language domain. In other words, something that are invariant across, for example, across different images. For example, given these two images, this region can be identically conceptualized as grass. Then that is the concept or the semantics. So image, that's a typical use cases in the domain of vision and the application of semantic segmentation. And the last one, The knowledge-based ones could be related to, say, the semiotics definition of the semantics. In other words, it deals with the contextual relationship. In other words, the interpreter is important in defining the meaning. And next, another limitation is that they are mostly focusing on one single relatively easy task. In other words, the reconstruction. In other words, the compression. So even if we have had extremely powerful capability in, for example, causal reasoning, we are utilizing that functionality for simply compressing your sending information. It can do much more than that. We can imagine and generate some images and predicting the future, looking back the past in a retrospective way, and many more. And then, as already partly mentioned, one limitation is that it lacks a notion of agent. So, for example, the third example, the knowledge-based example, presumes that everybody has the same and common and ideal, say, world model, rather than considering their different, heterogeneous and dispersed knowledge bases associated with each agent. And then, given these limitations and possible opportunities, and the backgrounds in the other relevant and neighboring, say, domains, I like to propose one architecture, which is not that say different from the existing words, but I try to explain each component in the from the perspective of what I have discussed. So, for example, the original Shannon communication model can be encapsulated in this simple form, on top of which we can add some, say, semantic coding, encoding and decoding module before and after the typical Shannon communication model, and upon which we can add another, say, knowledge model. And then this architecture is actually the third category of the current semantic communication frameworks. In other words, sharing one single common knowledge model across all of the listeners and speakers. Then here, one notable aspect is that the messages processed by the encoder or the decoder would be different from in terms of the type, are different from the one in the knowledge. In other words, knowledge are structured, and then knowledge includes some concept and general concept rather than your episodic experiences. So according to some human cognition model, it's a semantic memory is usually referred to something that are general knowledge rather than your episodic memories. And then same thing goes for reinforced learning scenario, where you play buffers towards your episodes rather than the information of knowledge obtained from those experiences are separated from each other. And then given this, we can split the knowledge and then also say each knowledge into each different agent. And accordingly, the knowledge is different. So given this, your sending information, your altered message might be differently understood by other, say, listener. So to compensate and to overcome these problems, synchronizing their knowledge bases would be important. It doesn't have to be the same, but at least you need to understand how my knowledge is different from your knowledge. Otherwise, the intended message delivery may not be guaranteed. So given this one, this way is a typical the communication direction. We can say that this is a foreground communication that is related to, say, latency sensitive, resource hungry, and many more. On the other hand, there may exist another paired communication for synchronizing your knowledge bases. It can be operating in the background. It does not have to be that latency sensitive. So on top of the foreground communication, there is we may need to consider the background communication of the knowledge rather than the single messages. So given this, to achieve this and to enable design this system two machine learning based semantic communication architecture, perhaps we may need to achieve several goals that are summarized as, say, 6 desiderata we want to achieve. some minimality for communication efficiency, yes. And then invariance over different communicating agents and or some tasks related specifics or nuances or channel variation and many more. And then disentangled, if your messages or meaning can be disentangled, which means that you can recompose something, and you can or you can the other direction, you can specify some other specific meanings. And then given this one, the many atoms of the concept that can be disentangled, you can then identify their causal relationships. And then given this causal relationship, you can do causal reasoning. But to make your causal reasoning effective and having an impact on your real world and or real task, then your concept should be emerged from the real environment or your real task. So the emergence of the or the groundness of your concepts and the relationship are also important. And then given this, you can generalize your causal relationship, the found causal relationship, so that you can construct the final knowledge, based on which you can communicate your knowledge with others on the background, and then you can finally achieve, say again, some minimality. In other words, improving the communication efficiency, and then skip unnecessary communication, or even do something more. Okay, then given these 6 desiderata, if you consider not communication scenario, only focusing on one single agent, then as an example, to achieve the invariance desideratum, one possible way in the context of machine learning and information theory could be regarded as an information bottleneck principle. So the traditional information theoretic approach to that is related to this aspect is rate distortion principle. So in that case, as we consider and focus only on the reconstruction task in the source coding, so to achieve the invariance is identical to minimizing the mutual information between your input and say your hidden message or the hidden feature, while maximizing the mutual information between your input and output. But if your task is no longer a reconstruction task, then maximizing the mutual information between here and there might be just useless. So instead, you can maximize not this relationship, but this one and that one. That leads to the information bottleneck principle. And then we can impose the information bottleneck not only by adding some penalty term in your, say, loss function in your machine learning optimization, but also you can physically introduce these types of bottleneck in the context of machine learning by imposing some bottleneck architecture, where the hidden layer dimension and or the width is smaller than your input dimension. That is a typical example in the autoencoder architecture itself. And then if we extend this direction and then consider multi-agent scenario, then to achieve invariance, perhaps discrete machine learning might be quite relevant. So as an example, we can consider, so most of the semantic communication systems and scenarios have, because it is we are at a very early stage, we've been focusing only on point-to-point communication, only one single pair. But if we consider multiple pairs, and then each of which has been trained and or experienced under a different environment, then given your trained encoder, the AI native transmitter, altering messages can only be decoded your originally paired decoder, but not like the others. The other decoder can only decode the messages and the meanings sent from the other originally paired and co-trained encoder. So one simple way, there may exist more sophisticated way, but one simple way to fix this problem is to first download the decoder from the other pair to the first transmitter, and then seemingly this transmitter can first fix all the model parameters such that this decoder, the other pair, will not change their model, and then this fixed model is now attached with my own transmitter. And then given this constructs another neural network model that can be separate further trained. In other words, if we first freeze and then retrain this model, then your encoder has potential in generating the message that is not only decoded by your original decoder, but also the others. And then actually downloading this model is quite similar to the federated learning operation in the context of distributed machine learning. On the other end, it's training across differently split encoder and decoder architecture by exchanging your forward activation and downloading the gradient is similar to the percept of split learning in the context of distributed learning. And then given this, we have done some simple example where there are two pairs of the encoder and decoder, and each of which is trained using different data sets, say MNIST data set and fashion MNIST data set. And given this, without applying this one, the original input image, the hand-drawn number 7 cannot be decoded by your the other side of the decoder, this one. Then if we freeze and retrain by downloading this model, then at least you can see a better picture. And then if you further exchanging some extra layers, in other words, downloading back from the encoder to the decoder, and then you can retain good performance even under the existence of some noise. And another way of achieving the invariance across multiple agents could be applying the, say, so-called neural augmentation algorithm, which can fusion some different modality of the output. For example, in the original neural augmentation algorithm, for the belief propagation context, here it combines the original model-based belief propagations algorithms output, and then another graph neural network-based machine learning-based output is now combined, simply linearly combined, and then that is fed into another module of the same architecture, belief propagation model, and then neural network architecture, and again in a recurrent way. In other words, recurrent neural network architecture. So passing through these operations, both even though their architecture and/or the model operations are totally different, the output is seamlessly fused the useful information from the model-based and then the other approaches. So similarly, we have considered these types of UAV control scenario where some target direction is moving in a circular way, while the objective is to hover multiple UAVs within this range as long as possible, while avoiding their inter-UAV collision within this very small area. So given this one, the collision event is, and then to make a decision for each agent, we utilize a attention network-based operation. In other words, simply speaking, one UAV agent is attending to its all neighboring UAVs, and then each of which has a limited field of view. In this case, given this information, that can be regarded as some state of the UAV. It makes a decision on its movement. And given this, here one important objective of this problem for each UAV is a collision avoidance. And the collision event is defined based on, say, relative distance rather than position. But when we measure the attention across different agents, then we can see that what I see is different from what you see me. That is undesired way, right? So given this diagonal line, you can see that these parts are not asymmetric, right? So to make it symmetric, which might be preferable for avoiding the inter-UAV collision, to solve this problem is applying this principle. So a bit outdated encoded message is downloaded to me, and then I jointly encoded these two messages into my next decision that is sent to another UAV and iterating this operation. Then we can achieve these types of, say, symmetric attention across different agents invariant to the location. And because our focus should be relative distance, not the location. And then we can see that the performance is better than, in terms of the total reward, better than the baseline algorithm. Okay, and then next we focus on other types of Desiderata that are the causality and the minimality in the context of context-dependent communication. So here we consider one pair of speaker and listener, and then here we assume that the speaker has a full knowledge of the listener's behavior. In other words, an ideal say neural network or any types of knowledge model. And likewise, the listener has a full knowledge of, assumed to also have the full knowledge of the speaker. In that case, each agent can play some virtual game in between their virtual counterpart, so that they can find out the best possible representation for, say, minimizing for communication efficiency in the context of the referential game. Referential game is a scenario where one entity is observed, and then that is mapped into some concepts, and then based on this concept that can describe that entity should be referred by the listener correctly. So in these operations, the speaker's say communication context is represented here. That transforms the observation into the concepts, and then the listener also converts their concept to the final entity. So given this architecture, we can solve some small iterative problem in a variational way, so that we can achieve. They can find a better representation that can represent the desired meaning and or the entity with small number of concepts that can finally reduce the bit length. Okay, and then here comes the final example that are related to this emergent and causal and general knowledge construction concept in the context of, say, protocol learning, which is to utilize the machine learning for learning control signaling messages. Actually, rather than the rules, but instead for the given rule, they're trying to create some new signaling messages that could be more efficient. So that problem has been formulated by utilizing some multi-agent reinforced learning frameworks, and then has been first proposed by the Jacobowitz group. Then actually the problem can be reformulated and summarized as one single neural network architecture, where we interpret some first part of the neural network connections and weights as say the user equipment part, and then the other parts are the shared components that can be interpreted as the base stations. And then likewise, the final part, again, the user equipment. And then the messages they are exchanging in between can be regarded and semantically interpreted as their control signaling messages. So while performing and solving this given some downstream task, for example, queue management and so forth, by taking the optimal actions, then because this is the neural net, one single neural network itself, so they're feeding forward information. In other words, the hidden activation might be useful for improving their performance. So in other words, to make it effective in its given downstream task. Then finally, these messages are emerged from the ground. So that's a way of achieving the protocol learning goal. And then our focus is not further improving the performance of this protocol, given protocol learning. Even though, for example, the scenario may include some unrealistic assumptions and too much simplification and many more, but just accept it, because of our focus is not to improve this operation. But given this one, our focus is that protocol itself should be interpretable and manipulated. But in this case, for every single simulation run, the emergent message will be different. And then we cannot even examine their characteristics, benefits, and cons on their given architect scenario and environment. And at the same time, for some cases, we may need some emergent messages and protocol, but that cannot be directly manipulated without retraining. It means that the role as a protocol might be a bit questionable. So our strategy is to first utilize the neural networks and deep learning's capability of identifying the hidden and complex relationship, but at the same time, we generalize their knowledge by unrolling and discovering their causal relationship of their generated and emergent message. For example, treating one trained neural network as a generator model by feeding some, because neural network is a function. So by feeding some inputs, it can generate some message, so some outputs. And then given this input and output relationship, by changing their input and output order, we can identify all the directional relationships. And then we also have identified that there are so many redundant messages. They are very close to each other in terms of the final actions and many more. So as an example, given this trained neural network can be unrolled based on all possible generated activations for the given available input states. This is the combinatorial possibilities of all possible combination. So upon which we can count the number of frequencies, so that each weight is associated with that frequency. So that can be treated as some probability. And given this, we at the same time, even though we can identify some relationship, for example, okay, given this state, the user equipment is trying to upload that message to the base station, uplink message, and then the base station, given this, and then the other user equipment uploaded messages, it tries to send the download message in the downlink, and then finally leading to this U is carrying out the decision. But we have identified that firstly, in the activation, these activations are generated by the neural network, but instead our intention of developing the protocol. So it includes so much redundancy, even though their value are slightly different. Their final, say for example, action would be the same as an example. So there are possibility of merging their uplink messages, and likewise we can merge the downlink messages. And then given this connectivity, we can identify their logical relationship, because the structure itself is providing some causal relationship. From the top, that's the causes, and then from the bottom and to the bottom there are the effects. So given this relationship, as long as the consequences, the effects are the same, then we can merge some redundant causes and many more. So in other words, we can also merge the connections. Combining all together, we can simplify the naively unrolled neural network protocol model into this very compact form. And then given compact form, one single edge is associated with the frequency generation. That can be regarded as a probability. So if we want, we can even calculate the uncertainty of this decision, in other words, entropy. And then we can even calculate the average uncertainty of this protocol model itself by calculating the average say entropy of this model as an example. So in doing so, actually this model and configuration is generated in a given environment. And then if it slightly change the environment, even though their statistics are the same, the generated neural network training neural network model will be different, and associated they say the symbolized model is also different. Then given these two models associated with the same environment, we can now compare these two models such that we can choose a better model in terms of their uncertainty as an example. So given this final model, we can, on the left-hand side, this is the original neural network model, and their performance has been measured in terms of the reverse learning rewards, the Q value. On the other hand, the right-hand side is the symbolized and approximate model, and we can see that their behavior are quite similar. And then given this one, because this symbolized model is extremely small, 1,000 times smaller than the original model, we can store the model for multiple different configurations as a portfolio. so that we can cope with different and time varying scenarios. This is an example. And the other one is that given multiple generated protocol models associated with the same environment, we can choose. You can think of choosing the best one. In other words, that can be regarded as some standardization, activities in terms of and in the context of this protocol learning. Then in this case, we as a baseline, we can choose the minimum number of omnic messages, the number of cardinality messages, and the minimum cardinality of the downlink messages, and selecting compared to these types of naive choice, it'll be there is a much more gain that can be obtained from choosing it based on the average, for example, uncertainty of the protocol model. And then given this one, if we, for example, encounter an emergency case where, for example, the second UE does not tolerate any collision, as an example. In this case, all the relationships are now revealed, so we can simply manipulate their connections in order not to avoid incur any collision. So if that is the specific objective, at the cost of compromising the accuracy, we can avoid the full collision for some cases. That's the last case example. So as a conclusion, this could be a bit beyond the semantic communication, and then if we can enable and achieve the say causalism capability, and then understanding the knowledge and then combining their knowledge synchronization through the background communication, and then corresponding foreground communication that are related to representative learning of the deep learning. And then we can choose some good architecture of the knowledge model, because all the operations are dependent on the knowledge base type. For example, if the knowledge base is a neural network, then their communication might be similar to the distributed machine learning. On the other hand, if the knowledge base itself is a symbolized model, then their communication will be totally different. And then the semantic coding itself is actually in this AI native architecture that is identical to the representative learning of the domain of machine learning and deep learning. And then given this knowledge base is exchanged and already received, how can you combine them together? How can we assimilate the received information? From my perspective, would be another important issue. And then thereby, how can we evaluate my and or the others' knowledge is also important in the domain of in improving your performance and or say pricing and many other issues. And then given this one, actually with the Yonsei group, they will present tomorrow in a separate, I'm not sure it is open discussion, but anyways, they will present some end-to-end operation use cases. So up until now, I have presented some fraction and basis of the possible examples toward achieving the final goal, but it does not include and show the end-to-end interplay and the operations. So possibly what the Yonsei group is now planning to implement one testbed demonstration showing the overall end-to-end operation under this architecture, where each agent in this remote control, intercontinental control scenario, where say sensor and actuator is associated with the local knowledge base. On the other hand, the remote control is associated with another knowledge base, and then they cannot be synchronized in real time. So it requires the communication across the knowledge bases. And given this communication, the received knowledge has to be assimilated. For example, one can simply always replace my knowledge with the others if I cannot trust my knowledge. On the other hand, otherwise, we need to first evaluate the received knowledge and then evaluate mine and then compare them together so that I can choose a better one. All right, and then here, the knowledge base type itself is important. Neural network or say symbolic network and many more. So given this one benefit of the symbolic architecture is, as partly shown in the protocol symbolization example, it allows you to manipulate as you wish. On the other hand, the drawback is that the symbolic method is normally difficult to construct from scratch from the real data, especially the data is complex, complicated, and multidimensional in that case. On the other hand, the neural network itself is quite good at identifying those types of and handling those types of complex data, but are on the other hand incapable of identifying the causal relationship and compromising some explainability, controllability. So probably the one possible way, from my perspective, is to combine them together. In other words, we can first train the deep neural network so that we can identify all possible hidden and explicit relationship in the given environment, and then we can treat it as a generative model so that we can identify the causal relationship upon which we can build and create another, say, symbolized knowledge base that can be regarded as a, say, knowledge transformation method from the deep neural to symbol. And then if we measure the effectiveness, one naive way is to measure the end-to-end performance. For example, is to reverse learning, just measure the reward. If this is the control example, then stability and many more. But that's too coarse to, for example, in our current communication design principle, we have more than several figure of merits. So likewise, to design these types of a bit ambitious communication architecture, we can also utilize at least the 6 Desiderata I have presented. So each of which, to achieve this goal, it requires some objective functions. If it's based on the neural network training, then training loss function is related to that function objective. So we can utilize those types of objective function to break the overall end-to-end operation into parts and then analyze it separately. And then I have currently in the symbolic example, I have actually explained one example based on one scenario where I can unroll all the input-output relationship in a deterministic way. On the other end, the standard way of handling these types of causal relationship in the context of the SOTA, the machine learning community, is to utilize a so-called structured causal model, which is a type of Bayesian network. So the key difference is that Bayesian network, the nodes are random variable. On the other hand, the one I have created, the nodes are just deterministic values. But there exists there is a relation between them. For example, this one can be regarded, this one can be regarded as an unrolled version of it. So if we can realize, we can expand all the realizations and calculate all the conditional probabilities, and then expand it together, then we can separate them one-to-one, and then that will result in these types of graph in the middle. But here, to enable this conversion, we may need to, at the same time, abide by some specific rules that is allowed within this Bayesian network architecture, for example, to abide by some Markovian property as an example. All right, and then this could be a bit beyond the scope of today's talk, but I'm personally interested in. So this is a visualization of the mathematical subject in archive 2017 or 19, I forgot that. 18. Okay, so given this, probably these parts of the subjects are the ones we are familiar with, say statistical theory, probability, optimization, spectral analysis, and many more. Okay, and then on the other hand, the other major part in the domain of mathematics is actually not the analysis, but algebra. So in the domain of algebra, the subjects are including the category theory, representative theory, logic, general topology, and many more. Perhaps they are more related to the notion of the semantics, and then their logical and structural relationships, and many more. So in that perspective, probably but algebra is not quantified. In other words, we are engineers. We need to quantify something and design and exploit it. So from that perspective, what we need to do is to borrow some key principles available in the domain of algebra into the analysis. As an example, category theory is one promising direction. So given this relationship, what I just explained, the structural causal model is like this one, and then some logical mathematical logic. The notable one, the first of logic is here, and then its description in programming languages like this, and many more. And the deep neural network is here, and then actually category a high-level category theory is capable of including everything within the same domain. So probably it might be able to provide some mapping relationship through the lens of some unification perspective. Okay, that's all I prepared. Thank you very much.